So what I've done here is I've done a lot of the math for you. Okay, since I've already gone over this stuff, I'm not going to spend a lot of time on the math. But I have my wood block from the start, and we know that this floats because its density is less than 1. But we're going to use Archimedes' principle to explain on a diagram how it floats. Okay, so I have this covered up because it's going to be part of the lab thing that I'm going to introduce you to. But the wood, it's 13 grams. Okay, so what I did is I took 13 grams and converted it to 0.013 kilograms, multiply it by 1.8, I mean, sorry, 9.8, and then there's our weight. Okay, the volume is 30.4 cubic centimeters. Okay, but what we have is our wood block in the water, and its weight pushing down is 0.13 newtons. What we need to figure out is what the buoyant force is pushing up. And the buoyant force is equal to the weight of this much water. And that's what I've done down here. So the weight of this much water, right, this much water is 0.3 newtons. So you can see the weight of the wood block going down is 0.13 newtons. The buoyant force, or the weight of the water that the block displaces, is 0.3 newtons. This number is higher than this one, so the block floats. It's an unequal force, so you have movement in the upward direction, which makes the wood block float. Okay, so I've done a lot of the math for you. You're going to want to copy this down if you want to give it a shot. What I've done, and you're going to want this. Okay, you're going to want these things, and I'm going to explain them in a minute. So if you want to pause it, you can pause it now and copy this stuff down. Okay, so go ahead and copy that down. Okay, so what I have here are two containers of equal size. Okay, one is filled with sand, one is filled with copper BBs. Okay, so I've already done all this stuff for you in the interest of time. So the mass of the sand is 0.057 kilograms. I've already converted it. Take that to multiply it by 9.8, gives me 0.56 newtons. And what I need to calculate the buoyant force is the volume of this object. How much water is this going to displace or push out of the way? So I've already done that for you, and this is all in your notes from metric system. The volume of this container is 38.9 cubic centimeters. Okay, so because of the same size, it's the same over here. These two objects have the same volume, obviously. It's the same container. So what's different is their mass, right? So I have 38.9 grams of water because I have 38.9 cubic centimeters or milliliters of it, which converts to 0.039 kilograms. Take that, multiply it by 9.8 meters per second squared, gives me that. So I have a volume of water that's 38.9 cubic centimeters that has a mass of 0.38 newtons. So what you can do, and what I'd like you to do if you want to give it a shot, is with this information, we already know, we're going to make this the sand example. I'll put it on the side so you can draw your diagram. And this would be a lab, one of the last labs we would do in 8th grade. And I'm pretty sure I'm the only one who does it too, so this might be the only opportunity you have to do a lab like this. Okay, and this is going to be the BBs, the copper. Okay, so I have my cylinder. And it's good to draw these diagrams. It really puts it, makes it easier. Okay, so what we have, because the objects are the same size, the buoyant force on each object is going to be the same. So I have my arrows pushing up, and my arrow pushing up, and for each one of these, it's 0.38 newtons. What I would like you to do is, actually I already gave you the answer, so I'll just go over it. So right here it's 0.56 newtons going down. Okay, so all right, it's going to sink. This number going down is higher than this one, and this one is 1.25 newtons. This one's really going to sink. Okay, now to find the final weight, the weight of these objects underwater, because you can calculate the weight of these objects underwater, you would do force net is force 1 plus force 2 So we'll say force 1 is the gravitational force. We could even say force gravity, force buoyant. That'd be even better. 0.56 newtons plus, now this is going in the opposite direction. Okay, direction has a positive and negative. So we've made down positive, we'll make up negative, plus a negative 0.38 newtons. And 0.56 minus 0.38 is 0.18 newtons. Okay, so let's do this one. Force net. Force buoyant. .25. Whoops. Negative, or plus a negative 0.38. That's your buoyant force. Equals, so 1.25 minus 0.38, 0.87 newtons. So let's try it. Okay, so what we have is our water. We have our water. I'm going to put this off to the side. Oh, actually, that works pretty good. Okay, so what we have now is, let's do the sand first. I have a scale. Okay, I'll put this up a little bit more. Okay, I have a scale. Okay, so when I put this on the scale, it should say, and this is only to the 10th. Okay, so it's probably going to say 0.2. But once I put this on the scale, this should go down to about right here, 0.2. So let's try it. Let's see. Let's see if we calculated the weight correctly. That's not too bad. It's like 0.3. Okay, which for a scale like this is actually pretty good. Okay, no, actually, let's see. Hold on a second. The sand should be 0.5. Oh, no, nope, it's stuck. It's 0.56 newtons. It's this number. Okay, now when I put it in the water, this is bent, shoot. When I put it in the water, it should be 0.2. Let's try it. Look at that, 0.2. Okay, so out of the water, 0.6 newtons. Wow, it's actually working really good right now. 0.6 newtons. Right, that's what we got here. Right, put it in the water, 0.2 newtons. Okay, so let's try the copper. Copper should be 1.25, right? 1.3, right? Because we only have tenths. So when I put this on the scale, it should say 1.3. Let's see how we did. It's pretty darn close. Okay, 1.3. When I put it in the water, it should be 0.9. Let's see. Wow, that's pretty good. Yeah, that's awesome. Okay, so it's not that the objects are the same weight underwater. It'll sink, but that just means that it's higher, but it's just going to be a lower weight. So what you can actually do is calculate the weight of an object underwater without having any water. All you need is some math, and the way to do that is by using Archimedes' principle. Okay, so I'm going to stop there, and if anyone is watching this video and would like some sample problems, if you could email me, that would be great. Otherwise, I hope you enjoyed it. Again, it's the hardest thing I teach. I hope you got something out of it. Okay, take care, everybody. Thanks for watching.